For decades, massive rocks appeared to glide unaided across a dry lakebed in Death Valley, leaving long trails behind them and generating theories that range from magnetic forces to supernatural causes, until careful field experiments revealed a surprisingly elegant, natural mechanism.
It's honestly one of the most fascinating geological puzzles of the last century. I mean, it literally tricked human observation for over 100 years.
It really did. So welcome to this deep dive. Today we are looking at Racetrack Playa, which is a place that looks and behaves like a prehistoric topographical anomaly.
Yeah, an environment so perfectly, strangely calibrated that it just defied explanation.
Exactly. Our mission today for you, listener, is to separate the empirical evidence from the folklore. We're going to unpack the precise, incredible physical fluid dynamics that finally solved this mystery.
And we are pulling from a really substantial stack of sources for you today to do that.
Right, we have deep geological surveys, peer-reviewed research papers from PLOS-1, and extensive field records from the National Park Service, plus some deeply detailed articles from the Smithsonian and various other scientific journals.
It really is a perfect case study of how the natural world can engineer phenomena that seem entirely impossible. Well, right up until you understand the highly specific, subtle physics at play.
Okay, let's unpack this, because the setting here is just as much a character in this story as the rocks themselves.
Oh, absolutely. The mechanism behind the movement of these stones is so dependent on its exact location. You really cannot understand the sailing stones without first understanding the extreme geography of Racetrack Playa.
Right, so we are talking about a location nestled high in the Panamint Range of Death Valley National Park in California. You are at an elevation of 11,132 meters.
Which is about 3,714 feet above sea level.
Yeah, and it is a completely isolated, bone-rattling drive down a primitive dirt road just to get there. And when you finally crest the mountains and look down, you see this massive, utterly barren expanse.
It's striking. It's what geologists call an endorheic basin.
An endorheic basin, meaning essentially it's a closed drainage system, right?
Right. Topographically, it's essentially a bowl. So water flows into it from the surrounding mountains, but there are no outflows.
No rivers or streams carrying water away to the ocean or another watershed.
Exactly. Because water cannot physically flow out, it can only leave through two mechanisms: evaporation into the dry desert air or slow seepage into the ground.
And over tens of thousands of years, this closed system creates a very specific type of floor. The playa itself is vast, measuring 4.5 kilometers long by 2.1 kilometers wide.
It's massive, and the floor of this basin is composed of this beige-colored clay and mud that is at least 1,000 feet thick.
Wait, 1,000 feet?
Yes. Think about that for a second. 1,000 vertical feet of pure accumulated sediment. It was laid down meticulously over 10,000 years of climatic shifts, specifically since the end of the last ice age.
That is just a staggering amount of mud. And during the dry season, which is almost all the time in Death Valley, that mud shrinks and bakes in the extreme heat.
Yeah, as the moisture evaporates, the immense tension in the drying clay causes it to crack.
Right, creating this endless, beautiful mosaic of hexagonal polygons that stretch as far as the eye can see.
But the defining physical characteristic of that surface, though, is its gradient. Or, well, rather, its almost total lack of a gradient.
It's incredibly flat, isn't it?
The playa is exceptionally flat. To put this in perspective, the northern end of this massive 4.5-kilometer basin is only 3.8 centimeters higher than the southern end.
3.8 centimeters. That's at a 1.5 inches.
Exactly. Across 4.5 kilometers.
Which is practically a rounding error in geology. I mean, that is an almost imperceptible slope.
It really is. And it's maintained by the episodic deposition of ultrafine-grained sediment. When water does wash down from the highlands, it carries suspended silt and clay.
Because the basin has no outlet, the water just sits there, completely still.
Right, and that allows the very finest microscopic particles to settle perfectly evenly across the entire expanse before the water evaporates. It essentially self-levels over millennia.
But if it's a completely enclosed basin in one of the driest places on Earth, where does the water come from to do this self-leveling? And why is that extreme 3.8 centimeter flatness so crucial to the phenomenon?
Well, the rain shadow effect created by the surrounding peaks is a big part of that. To the west, you have Ubahibi Peak rising over 5,600 feet, which acts as a massive atmospheric barrier.
Because Death Valley is famous for receiving practically no rainfall, right? Often less than 2 inches a year.
Exactly, because these mountains force approaching weather systems to rise. As the air rises, it cools and drops its moisture on the western slopes before it ever reaches the valley.
But during rare, severe winter storms, precipitation does make it over the mountains, either as rain or snow.
And because the basin is endorheic, all that sudden runoff washes down the steep, rocky slopes and pools directly onto the playa floor.
So if we look at the physics of that water hitting the playa floor, because it is unbelievably flat, the water doesn't just form a deep puddle in one corner.
Right, like it would in a normal valley. It spreads.
The lack of gradient means even a tiny amount of water, say just half an inch of rainfall, spreads out perfectly evenly across the entire 4.5-kilometer stretch.
It creates a massive but very shallow ephemeral lake. And this is where the physical properties of that specific clay come into play.
Because the mud beneath that water is composed of those ultrafine particulates. When dry, it's like concrete.
But when saturated, it undergoes a radical transformation. The water is absorbed between the microscopic clay platelets, acting as a lubricant. The coefficient of friction drops dramatically.
So when that ultrafine clay gets wet, it behaves less like mud and more like hydroplaning on a highway.
Yeah, the water creates a microscopic barrier between the rock and the clay underneath it. It effectively deletes the friction that normally keeps heavy objects anchored to the ground.
Precisely. The mechanical interlocking between the rock's surface and the ground is virtually eliminated by that boundary layer of slick, saturated clay.
So the stage is set. We have a perfectly flat, isolated basin that occasionally, briefly, turns into a shallow, near-frictionless surface.
Now we have to introduce the enigmatic actors that perform on this stage, the rocks themselves.
Right. When you walk out onto the southern end of the playa, you see hundreds of these stones speckling the cracked clay.
And geologically speaking, we know exactly where they come from. They aren't native to the deep clay playa floor itself.
No, the geological surveys outline two primary lithological types out there. First, you have dolomite.
Now, dolomite is a sedimentary carbonate rock, similar to limestone, right? And out here, they appear as these sub-rounded blue-gray stones with distinct white bands running through them.
Exactly. And these originate from a steep, 260-meter-high Paleozoic cliff that flanks the eastern shore at the southern end of the basin.
Paleozoic, meaning that cliff face dates back hundreds of millions of years.
Formed in ancient marine environments before being uplifted by tectonic forces. And the cliff is constantly subjected to extreme temperature fluctuations, blistering heat during the day, freezing cold at night.
This thermal stress, combined with occasional frost shattering where water gets into cracks and expands as it freezes, causes blocks of this dense dolomite to break off.
Right, and they tumble down the scree slope onto the flat playa surface below.
Okay, and the second type of rock out there is syenite, which is a tan-colored, feldspar-rich, igneous rock.
To unpack that, syenite forms from magma that cools slowly deep underground. And it's rich in feldspar, which is a silicate mineral that tends to fracture along flat plains.
This gives the syenite rocks a specific, often more angular geometry compared to the rounded dolomite.
Yeah, and these syenite rocks tumble down from the adjacent western slopes of the basin. But the key point is that once gravity delivers both types of rock to the flat edge of the playa, they're entirely isolated from their
The
source.
slope ends entirely, and they are not small pebbles. We're talking about high-density rock.
They range from the size of a computer mouse to a microwave oven. Some of them are massive, intimidating boulders.
Yeah, the most famous rock out there, which researchers playfully named Karen, weighs estimated 320 kilograms.
That is a 700-pound block of solid dolomite.
Which brings us to the visual evidence that made this place a global curiosity. Because behind many of these rocks, scored directly into the hard-baked clay, are trails.
These tracks are essentially shallow furrows, usually 8 to 30 centimeters wide, and typically less than 2.5 centimeters deep.
But it's their length that is staggering. Some of them stretch up to 224 meters.
That is over 2 football fields in length, carved by a single rock.
And the track morphologies, the actual shapes they trace into the ground, are what really capture the imagination and confound logic.
If you walk along them, they don't seem to follow a uniform physical rule at all.
You have some tracks that are perfectly straight lines, as if drawn by a surveyor's ruler. Others curve gracefully in wide, sweeping arcs.
Some make sharp, incredibly abrupt 90-degree turns without any deceleration curve. Some literally stop, reverse direction, and double back exactly on themselves.
The researchers also noted distinct textural differences in the tracks based on the physical geometry of the rock itself.
Yeah, rocks with rough, jagged bottoms, often those angular syenite blocks we mentioned, tend to grip into the mud more firmly, acting like a keel on a boat.
So they leave these remarkably straight, deeply striated paths.
Conversely, rocks with smoother bottoms, which have a lower coefficient of friction against the mud, offer less directional resistance. They tend to wander and drift, leaving more erratic, winding trails.
Now, if we think about this logically, based on what we've established, someone might assume, okay, these rocks tumble down from the mountains due to gravity. If they're already on a downward trajectory, couldn't gravity just be continuing the job? Over decades, with rain making the ground slick, could gravity just be slowly sliding them down a gradual slope?
That is the most intuitive first guess. But what's fascinating here is that if we connect this to the broader topographical data we discussed earlier, we can completely mathematically rule gravity out as the driver.
Remember that 3.8 centimeter elevation difference across 4.5 kilometers.
The northern end of the playa is actually higher than the southern end. Because the vast majority of these rocks originate at the southern cliffs and travel north, they are actually moving uphill.
Uphill. That is the detail that completely breaks the casual observer's brain. You have a 700-pound rock carving a 200-meter trench uphill across a flat desert.
It proves undeniably that there has to be a powerful external kinetic force at play. Gravity alone cannot push mass up an incline no matter how slick the mud is.
And it is that exact contradiction, the presence of massive physical displacement without an obvious physical mechanism, that fueled decades of wild speculation.
Human beings have a deep-seated psychological need to fill the void of the unknown with narrative explanations, you know? When empirical science doesn't have an immediate answer, folklore rushes in.
And Racetrack Playa provided a massive blank canvas for that, because early scientific tests proved wind alone couldn't do it, and gravity was ruled out by the elevation data.
So the theories that sprang up among the public were incredibly creative. You had early prospectors and mid-century tourists proposing everything from UFOs and alien intervention to supernatural energy fields.
There was intense talk of magnetic vortexes beneath the Earth's crust out there, or some sort of localized gravitational anomaly. You even had some fringe theorists citing the Tristan effect.
The Tristan effect, just for context for you listening, is a highly speculative, unverified hypothesis floating around in fringe circles regarding magnetic levitation and localized distortions in the Earth's magnetic field.
Right, and it's often misapplied to geological anomalies where heavy objects appear to defy standard gravity.
And it's crucial for us to clearly separate those unverified hypotheses from empirical science. There is absolutely zero geological, magnetometer, or physical evidence to support magnetic vortexes.
Or extraterrestrial involvement, or localized gravity wells on the playa. But the folklore itself became a tangible problem for the National Park Service.
It became a major issue of conservation, because people started to genuinely believe the rocks possessed some inherent magical or magnetic property.
Park rangers started dealing with a growing, destructive problem of tourists hiking out to the extremely remote playa and stealing the stones.
Hoping to take a piece of that mystical energy home to put on their mantelpiece.
Which is incredibly tragic, because as the rangers point out, the moment you take the rock off the playa, all the perceived magic is lost. It's just a chunk of dolomite.
Worse, removing them completely ruins the natural phenomenon for everyone else, destroys a delicate natural landscape, and actively disrupts ongoing scientific studies tracking specific rocks.
The scientific community, meanwhile, was equally frustrated by the mystery, though for entirely different empirical reasons. They wanted a mathematically sound answer.
The first formal, documented investigation was launched in 1948 by two geologists from the U.S. Geological Survey, Jim McAllister and Alan Agnew.
They mapped the area, documented the tracks, and proposed that dust devils, the intense localized thermal whirlwinds that are common in deserts, might be catching the rocks and spinning them.
Which sounds vaguely plausible until you look at the math for a 700-pound boulder. A dust devil is a thermal updraft. It has high rotational speed, but very little broad horizontal thrust.
The wind velocity required to overcome the static friction of a 320-kilogram rock, even on wet clay, is staggering.
To test the wind theory directly, in 1953, a geologist named John Shelton decided to bypass the theoretical math and perform a physical experiment.
He literally landed a small aircraft directly on the dry playa surface, parked it in front of a rock, and revved the engine to maximum throttle.
He blasted the rock with hurricane-force winds from the propeller. That produced thrust equivalent to a 70-mile-per-hour sustained gale.
So if wind alone couldn't move a 700-pound rock, because Shelton's airplane propeller proved that even hurricane-force winds couldn't move it, scientists realized they were missing a vital ingredient.
Shelton's test was also flawed fluid dynamics, right? Prop wash from a plane is highly turbulent, chaotic airflow. whereas natural atmospheric winds are more laminal, broad, sweeping sheets of force.
But even taking that into account, the pure wind hypothesis stalled out. They realized they needed a mechanism that either massively increased the surface area catching the wind or massively decreased the resistance of the rock.
They had to look at ice. Which brings us to the 1970s and what remains one of the most dedicated yet tragically misinterpreted field experiments in the history of this mystery.
Two geologists, Robert Sharp from Caltech and Dwight Carey from UCLA, decided to settle the debate through sheer attrition.
They set up a rigorous monitoring program that lasted 7 long years. They selected 30 specific stones, gave them names, this is where Karen comes from, and meticulously tracked their precise coordinates twice a year.
Camping out in the freezing desert winter and blistering summer. Their primary goal was to test the leading hypothesis of their era, which was ice rafts.
Geologists knew from weather data that the playa occasionally flooded and then froze during the harsh winter nights.
The logical deduction was that the rocks were getting embedded in large, solid sheets of ice. When the wind blew, it wasn't pushing a small rock, it was pushing an enormous, solid ice sheet.
That acted like a massive sail, dragging the rocks embedded in its underside across the mud. To test this, Sharp and Carey designed a physical trap.
They hammered a corral of thick iron stakes deep into the hard clay surrounding a specific rock.
They spaced the stakes closely together, but with enough room for the rock to theoretically pass through if it moved independently.
So if they bolted the rock in with iron stakes, I assume they were waiting to see if a glacier-thick sheet of ice would form around the rock and the stakes and then just rip the iron stakes right out of the ground. Did putting the rock in jail solve the mystery?
No, the result was entirely counterintuitive to their hypothesis. When they returned months later to check the corral, the rock had escaped.
Wait, really? It got out?
It had moved entirely outside the iron perimeter, leaving a fresh trail in the mud. But the iron stakes were completely undisturbed. They hadn't been bent, pulled, or loosened.
Wow.
Furthermore, through their detailed surveying, they noticed that the distance between multiple moving rocks changed as they traveled.
Right. If they were frozen in a block, the whole block moves as one unit. The coordinates between rock A and rock B shouldn't change.
Exactly. If 3 rocks were locked in a single, rigid sheet of ice, their relative distances to each other should have remained perfectly constant as they slid down the playa.
But they were moving independently. They were diverging, crossing paths. So Sharp and Carey looked at that specific evidence, the undisturbed stakes and the changing relative distances, and concluded, well, it can't be a solid ice sheet.
And this raises a profound point about the philosophy of science and the danger of underlying assumptions. Sharp and Carey falsely concluded that ice couldn't be the cause.
Because their mathematical and physical models assumed the ice would have to be a thick, monolithic, rigid block, essentially a miniature glacier.
They couldn't conceive of an ice mechanism that wasn't structural and solid. That single misinterpretation of phase dynamics stalled the true answer for decades.
It sent everyone completely back to the drawing board. It was a massive red herring. If it wasn't wind alone and it wasn't rigid ice acting like a glacier, what unseen hand was moving the stones?
To solve a mystery that stumped the 1970s researchers, a new generation had to approach it, applying immense patience, millions of dollars of funding, and some seriously upgraded, custom-built modern technology.
Enter the Slithering Stones Research Initiative.
This initiative took shape over several years. It was heavily pioneered by Richard Norris, a paleobiologist at the Scripps Institution of Oceanography, and his cousin James Norris, who is a mechanical engineer.
But the modern technological foundation was laid a bit earlier by Ralph Lorenz, a planetary scientist from Johns Hopkins University.
Right.
What was a planetary scientist doing in Death Valley?
In 2006, Lorenz was actually using Death Valley as an extreme weather analog for Mars. He was out there setting up miniature, highly sensitive weather stations to model atmosphere conditions on other planets.
And in the process, he became fascinated by the stones. He started running fluid dynamics models on how buoyancy might play a role,
drawing direct parallels to ice-rafted boulders he had studied on Arctic coastlines.
The Norrises eventually teamed up with Lorenz and a few others to form this initiative with one goal: catch the rocks in the act, stop deducing from the aftermath, and observe the event in real time.
But there was a massive logistical catch. Because Racetrack Playa is a heavily protected wilderness area within a national park, the Park Service explicitly prohibited them from touching, altering, or tagging the native rocks.
They couldn't drill into the natural dolomite to insert sensors.
So James Norris, applying his engineering background, devised a brilliant workaround. They went well outside the park boundaries to Darwin Canyon and quarried Permian-aged limestone blocks.
They specifically selected limestone that possessed the exact same mass, density, and friction coefficient as the native dolomite rocks on the playa.
The same accelerometer and GPS technology sitting in your smartphone right now, the stuff that tells your Maps app which way you're facing, is exactly the kind of microtech the Norris cousins had to hack.
And embed inside a solid block of rock.
Yeah.
But they had to engineer it to survive one of the most hostile environments on Earth. Here's where it gets really interesting.
Precisely. They used heavy concrete coring tools to hollow out a precise cavity inside each quarried limestone block. Inside, they embedded custom-built, motion-activated GPS loggers engineered by James Norris's firm.
The engineering challenge here was immense. How do you build a battery and a sensor array that can survive freezing desert nights of -5 degrees Celsius, followed by blistering daytime heat?
And do so for years on end without maintenance. They had to heavily insulate the cavities, using the thermal mass of the rock itself to protect the electronics.
And program the GPS to remain in a deep sleep state, drawing microamps of power, until an internal accelerometer detected sustained movement.
So they construct these incredibly heavy, GPS-equipped smart rocks. They haul them out to the playa in the freezing winter of 2011.
They install a high-resolution weather station to log wind velocity, ambient temperature, insolation, which is solar radiation, and rainfall at 1-second intervals.
They set up ultra-high-definition time-lapse cameras on the cliffs overlooking the basin, and then, well, they just wait.
Ralph Lauren's famously joked during an interview that this was going to be the most boring experiment in the history of science.
Because remember, the historical data showed that these movement events are exceptionally, frustratingly rare. Years, sometimes decades, can go by without a single rock moving a millimeter.
You need an almost impossible alignment of environmental factors. We are talking about a perfect storm, and they waited over 2 years. From the winter of 2011 to late 2013, absolutely zero rock movement.
Think about the dedication required for that. Securing the grant funding, explaining to the university why nothing has happened, hiking out into this desolate, freezing basin 5 to 8 times a year just to swap out lithium battery packs.
Staring at expensive rocks that are literally doing nothing.
As Richard Norris noted, this was essentially science for the fun of it. They weren't going to cure a disease or invent a new commercial product. They were doing it because it was a beautiful, complex puzzle of physics.
And their immense patience paid off in the most spectacular cinematic way possible on the morning of December 20, 2013. In a stroke of astronomical luck, Richard and James Norris were physically present at the playa.
Checking the weather instruments and replacing batteries.
They were standing right there on the ice. They were the first human beings in recorded history to definitively see it happen.
Yes. They witnessed over 60 rocks moving simultaneously across the playa. The time-lapse cameras caught it visually. The internal GPS loggers woke up and recorded the exact speeds, headings, and trajectories of the smart rocks.
And the weather station logged the precise second-by-second atmospheric conditions that triggered it. After over a century of guessing, folklore, and failed experiments, the mystery was solved.
By direct, undeniable observation and a mountain of hard data. And the data revealed something stunning. It turns out, nature doesn't need supernatural forces or hurricane winds.
It just needs an impossibly elegant recipe of subtle physical conditions aligning perfectly.
That recipe is highly specific. The fluid dynamics at play require 4 distinct chronological conditions. If any one of these conditions is missing or happens out of sequence, the rocks do not move.
So if wind alone couldn't move a 700-pound rock, and a solid glacier would have ripped the iron stakes out, we're looking for a middle ground. Let's deduce the physics here. First, you need the lubrication we talked about earlier. You need water.
Step 1 is indeed shallow water. A rare, intense winter storm must dump just enough precipitation to flood the playa. But the specific depth of the water column is highly critical.
Right, it must be between 3 and 10 centimeters deep.
It has to be deep enough to allow a layer of ice to form and float freely above the mud, but shallow enough that the upper portions of the rocks, especially the large boulders like Karen, remain exposed above the waterline.
Okay, so you have a freezing puddle across 4.5 kilometers, with the tops of the rocks sticking out like little islands. Then the temperature has to drop dramatically.
Which brings us to step 2, window pane ice. As nighttime temperatures plummet well below freezing in the desert winter, an ultra-thin layer of ice forms across the entire surface of the shallow lake.
This is the crucial deviation from Sharp and Carey's 1970s assumption. This is not the thick, rigid block of ice they imagined.
This is technically known as window pane ice. It is specifically between 3 and 6 millimeters thick, about a quarter of an inch.
It's basically the thickness of the glass in a cheap picture frame. Just thick enough to hold its shape structurally across a wide area, but thin enough to be incredibly fragile.
Precisely. Step 3 involves phase transition dynamics triggered by thermal energy, the late morning thaw. As the sun rises over the Panamint Range, it beams intense solar radiation down into the basin.
The continuous quarter-inch sheet of ice begins to warm, melt, and structurally fail. Because of the sheer scale of the playa, the ice sheet fractures into massive floating panels.
Some of which are tens of meters across.
So now we have giant floating panes of glass-thin ice sitting on top of a few inches of frictionless water. And step 4 provides the actual kinetic push.
Step 4 is light winds, and this is the most beautiful part of the mechanism. You don't need Shelton's hurricane-force propeller. You just need a steady, relatively light breeze of about 3 to 5 meters per second.
Which equates to roughly 10 miles per hour. Let's break down the physics of why a 10-mile-per-hour breeze can move a 700-pound rock. Think about a sailboat.
If you have a massive panel of floating ice that is 50 meters wide and 50 meters long, it has an enormous surface area. Even a gentle 10-mile-per-hour breeze hitting that vast expanse of surface area transfers a massive amount of kinetic energy.
The ice panel catches the wind like a giant, horizontal, rigid sail.
Exactly. The wind transfers its kinetic energy to the ice panel. The ice panel, floating on the water, begins to drift. Beneath the ice and water, the ultrafine clay is completely saturated, dropping its friction coefficient to near zero.
As the massive ice panel drifts, its leading edge encounters the exposed top of a rock protruding above the water.
The ice acts like a bulldozer blade. The collective force of the wind pushing against the immense surface area of the ice is concentrated entirely onto the side of the rock.
It easily overcomes the remaining static friction, slowly, relentlessly shoving the heavy stone across the slick clay.
But it's happening so slowly. The GPS data from the smart rocks showed they were moving at speeds of just 2 to 5 meters per minute. That is a few inches per second.
If you're standing on the shore of this massive 4.5-kilometer lake, looking at a rock hundreds of meters away, moving at 2 meters per minute, well, you wouldn't even notice it's moving. It would look completely stationary to the human eye.
That is the optical illusion that protected the secret for so long. The surrounding water is rippling in the wind, the ice panels are drifting and glaring in the sunlight. Everything in the visual field is in subtle motion.
The human eye cannot easily lock onto the movement of a solitary gray stone against that vast, uniform, shimmering background at such a slow speed. That is why no one saw it for a century.
Furthermore, the tracks are forming entirely underwater, hidden beneath the ice panels and the muddy water. It is only weeks later, when the lake completely evaporates and the mud bakes dry in the sun, that the deep, scored trails are revealed to the naked eye.
It is brilliantly, elegantly simple. But wait, how does this specific mechanism, thin ice and light winds, explain the 1970s corral experiment where the rocks escaped the iron stakes?
This is where understanding the exact material properties of window pane ice is crucial. Because we're dealing with millimeter-thick ice, not a rigid glacier, it is subject to brittle failure when it encounters a point load.
When a massive, drifting ice panel encounters a rigid, immovable obstacle, like an iron stake hammered deeply into the hardpan, it doesn't stop.
And it doesn't rip the obstacle out of the ground. Because it is incredibly thin and fragile, it shatters upon impact.
Oh, the fluid dynamics of brittle failure. It just breaks apart around the obstacle like glass hitting a rock.
Precisely. The kinetic energy of the ice panel exceeds its own structural tensile strength. It fractures into thousands of small, harmless ice chips.
So, in Sharp and Carey's corral experiment, the large ice sheet hit the thick iron stakes and immediately shattered at the point of contact. The stakes didn't move because the ice wasn't strong enough to pull them.
However, a surviving panel of ice, perhaps just a few feet away, continued to drift past the stakes. The edge of that surviving panel caught the rock inside the corral and slowly pushed it out through an opening in the stakes.
Meanwhile, a neighboring rock might be sitting directly in the wake of the shattered ice.
That perfectly explains the changing distances. One rock gets caught by the leading edge of a massive intact panel and gets dragged 50 feet, but the rock right next to it is sitting in a pile of crushed ice chips.
From where the panel broke against an obstacle, the crushed ice exerts no kinetic force, so that second rock sits perfectly still.
And when the wind shifts slightly, causing the giant ice panel to slowly rotate on the water, the rock it's pushing changes direction, creating those sharp, unnatural 90-degree turns.
Exactly. The mechanism is entirely dependent on the chaotic fracturing and rotation of these thin ice panels. The researchers noted that these highly specific conditions might only align for a few minutes every decade.
It is a profound testament to the fact that in geology, you don't always need massive, violent, cataclysmic events to create profound changes on the landscape.
So what does this all mean? It perfectly illustrates how patient scientific observation strips away the folklore to reveal something far more fascinating. The sailing stones prove that nature doesn't need magic or aliens to do incredible things.
It just needs the right alignment of subtle physics. And looking at the sources we gathered for this deep dive, this exact pattern, where a seemingly impossible natural phenomenon generates wild mythology until rigorous physics explains it happens all over the world.
There are other environmental anomalies that look like magic, but are actually masterclasses in environmental science.
A fantastic, deeply studied comparative example is found in Alberta, Canada at Abraham Lake. During the harsh winter, the lake freezes over.
But trapped within the exceptionally clear ice are what look like thousands of white, frozen jellyfish stacked in perfect vertical columns descending into the dark water.
They are visually stunning. Historically, some indigenous folklore in Arctic regions viewed similar sudden releases of gas or strange formations in frozen lakes as the breath of subterranean spirits.
Or demons trapped beneath the ice trying to escape. But the reality isn't spiritual, it's heavily biochemical. The process is called methanogenesis. Let's break down the thermodynamics and biology of this.
Abraham Lake is actually an artificial reservoir, created in 1972 by the construction of the Bighorn Dam. When they flooded the valley, they submerged massive amounts of trees, vegetation, and organic topsoil.
At the bottom of the lake, in environments that are completely devoid of oxygen, you have specialized anaerobic bacteria.
Specifically, these are methanogens. In the absence of oxygen, these archaea use anaerobic respiration to metabolize that massive layer of decaying organic matter at the lakebed.
As a byproduct of their digestion, essentially as waste, they excrete large volumes of methane gas. Because methane is highly buoyant, significantly lighter than water, it forms bubbles that detach from the lakebed and rapidly float toward the surface.
During the summer, these bubbles reach the surface, pop, and the methane escapes into the atmosphere invisibly. But the physics change drastically in winter.
Right, because we have to look at the thermodynamics of how a lake freezes. Water has a unique density anomaly. It is most dense at 4 degrees Celsius.
As the winter air cools the surface water, it gets denser and sinks, pushing warmer water up. Eventually, the entire water column reaches 4 degrees.
But as the surface water cools further, down to 0 degrees, it actually becomes less dense. So the freezing water stays on top. This means the lake freezes from the top down, creating a lid of ice while the water beneath remains liquid.
Exactly. The ice sheet acts as an insulator. So down at the bottom, the methanogens are still active, still producing methane. A bubble releases and rises.
But now when it reaches the surface, it hits the solid frozen bottom of the ice sheet. It cannot escape. Because of the upward pressure of its own buoyancy pushing against the flat ice, the bubble flattens out into a disc shape.
And this is where the thermal conductivity of the ice comes into play. The freezing air above the lake continues to pull heat out of the water below. The ice sheet grows thicker, freezing downward into the liquid water.
As the freeze line drops, it encapsulates that flattened methane bubble, locking it solidly in the ice.
Then, a few hours or days later, another bubble rises from the exact same spot on the lakebed because the bacteria are clustered around a specific food source. It hits the new, lower bottom of the ice sheet, flattens out, and gets frozen in place.
Over the course of the long winter, as the ice grows several feet thick, this repetitive process creates these perfectly stacked vertical columns of frozen methane disks.
It's beautiful, but as the researchers point out, it's also incredibly dangerous. If you go out on the ice and drill into one of those columns with an ice auger and you happen to light a match, a massive plume of fire will shoot out because methane is highly combustible.
If we connect this to the bigger picture, studying these trapped bubbles at Abraham Lake provides vital, actionable data for climate scientists.
By understanding the precise rates at which methane is produced, trapped, and released in these specific artificial reservoir conditions, researchers can build highly accurate mathematical models.
They use these models to understand the far more severe global impacts of permafrost melting in the Arctic, which threatens to release billions of tons of ancient, trapped greenhouse gases into the atmosphere as the planet warms.
It takes the localized magic of frozen jellyfish and turns it into highly actionable global climate science.
But I want to spend some serious time on one more anomaly from our sources that is just as fiercely debated today as the sailing stones were in the 1970s. We're talking about the fairy circles of the Namib Desert in southern Africa.
This is one of the most compelling ongoing debates in modern ecology. If you fly over the arid grasslands of the Namib Desert, you see millions of perfectly circular, barren patches of red soil.
They range from 2 to 15 meters in diameter. Each circle is completely devoid of vegetation in the center, just bare dirt. But it is ringed by a distinct fringe of unusually tall, healthy, vibrant grass.
When viewed from above, it looks exactly like a massive, mathematically perfect honeycomb or polka dot pattern stretching across the landscape for hundreds of kilometers.
The local folklore surrounding this is rich and perfectly understandable. The Himba people, who are indigenous to the region, traditionally believe these circles are the literal footprints of their gods left on the earth.
Or perhaps patches of soil burned away by the venomous breath of a subterranean dragon moving beneath the crust.
And honestly, standing in the middle of a desert, looking at millions of mathematically perfect circles, you can absolutely see why human intuition reaches for gods and dragons.
But modern science is currently locked in a massive high-stakes debate over two competing, purely physical theories to explain them. The first major theory is the sand termite hypothesis, championed heavily by biologist Norbert Jurgens.
This theory views the circles as massive engineered ecosystems. In a desert where rainfall is incredibly scarce, the theory suggests that colonies of sand termites actively engineer the landscape for their own survival.
They systematically eat the roots of the short-lived grasses within a circular zone, killing the plants and creating the bare patch.
But why would they deliberately destroy their own food source? That seems counter-evolutionary.
It's actually a brilliant strategy of hydraulic engineering. Plants act as moisture pumps, they pull water out of the soil and release it into the air through transpiration.
By killing the grass in the center, the termites stop this water loss. When the rare rains do fall, the water hits the bare patch.
Without plant roots to absorb it, the water percolates deep into the porous, sandy soil, sinking far below the intense heat of the surface sun where it would evaporate.
So the termites are basically building a massive subterranean water reservoir protected by a layer of dry sand on top.
Exactly. They use their saliva to cement the sand grains together deep underground, increasing the soil's moisture retention. This subterranean water slowly diffuses outward through the soil via capillary action.
This outward seeping of water provides a constant, reliable moisture source to the grasses on the outer periphery of the circle. That's why the fringe grass grows so unusually tall and strong. It's being constantly irrigated by the termite reservoir.
The termites then feed on the roots of this perennial fringe grass, surviving brutal, multi-year droughts that kill off the rest of the desert vegetation.
It's an incredible city-scale display of insect engineering. It makes perfect logical sense. But the competing theory is entirely different and mathematically mind-blowing.
It argues that there are no insects involved at all, and it's based on Turing patterns.
Yes, Turing patterns, named after Alan Turing, the legendary mathematician who cracked the Enigma code during World War II. In 1952, Turing proposed a mathematical model to explain how complex patterns in nature, like the stripes on a zebra or the spots on a leopard, could arise naturally from a homogeneous starting state without any external blueprint.
He called it a reaction diffusion system.
Let's break down how Alan Turing's math applies to a desert in Africa. The Turing model relies on two competing variables, an activator and an inhibitor. In the Namib Desert, the theory argues that the grasses themselves are engaged in a brutal life-or-death competition for scarce water.
Precisely. In this model, a strong, established patch of grass acts as the activator. It develops a massive, deep root network that aggressively pulls water toward itself from the surrounding soil.
This allows the plant to grow larger, which in turn allows it to grow an even wider root system, drawing even more water.
A positive feedback loop. But the consequence of that activator pulling all the water is the inhibitor. By sucking the surrounding soil dry, the strong grass creates an intense zone of moisture depletion, a dead zone in a wide radius around itself.
In this dead zone, the soil is so dry that new grass seeds simply cannot germinate or survive.
And this is where the math gets beautiful. The plants aren't consciously communicating, but their mechanical action of drawing water forces them to space themselves out perfectly.
If two strong plants grow too close together, their dead zones overlap, they exhaust the water supply, and one or both die.
The mathematical models for this intense resource scarcity and spatial competition predict that the vegetation will naturally, automatically organize itself into a hexagonal honeycomb pattern of bare spots surrounded by vegetation.
Which exactly matches the geometric distribution of the fairy circles seen from satellite imagery. And this debate between the termite engineer and the Turing mathematicians was thrown into absolute chaos recently by a discovery on a completely different continent.
Researchers found identical, mathematically perfect fairy circles in the remote outback of Western Australia. They look exactly the same as the ones in Namibia.
And when a team of researchers went to the Australian circles and dug extensive trenches to search for the cause, they found absolutely zero evidence of termite activity. No nests, no salivary cement, no chewed roots, nothing.
This discovery heavily reinforces the Turing's self-organizing vegetation theory, suggesting that under extreme water stress, grasses will naturally form these exact spatial patterns regardless of the continent or the presence of insects.
Though, to be fair to the sources, many biologists studying the Namibian circles still fiercely maintain that while Turing patterns might explain Australia, in Africa, the termites are physically present in the circles and play a crucial symbiotic role in maintaining the soil moisture.
The debate is ongoing. And that is the beauty of the scientific process. Whether we are talking about the freezing fluid dynamics of Death Valley, the anaerobic chemistry of Abraham Lake, or the mathematical ecology of the Namib Desert, human beings have an innate, powerful tendency to immediately fill the void of the unknown with aliens, dragons, and magic.
The human brain dislikes mystery. But when you actually take the time to observe, when you spend years engineering GPS units to survive freezing temperatures, when you study the thermodynamics of ice formation or model the fluid dynamics of a shallow pond, the true physical reality is actually much cooler and much more satisfying than the myths.
It shows that the universe operates on a set of incredibly complex, perfectly balanced rules. It is a profound reminder that the natural world is immensely complex and fundamentally logical.
And the research doesn't stop at solving a localized mystery. The sailing stones mechanism is now actively helping researchers understand broader critical phenomena.
For example, the mathematical models of how thin ice pushes heavier rocks are being used to study the dynamics of ice rafting in the Baltic Sea and how massive amounts of sediment and rock are moved in Arctic shallow water environments.
Which directly impacts shipping lanes and coastal erosion. The solution to one localized, seemingly trivial mystery often unlocks vital tools for understanding massive global systems.
Which perfectly summarizes the core takeaway for you, our listener, today. The Sailing Stones of Death Valley offer a masterclass in the necessity of patient, rigorous scientific observation.
The kinetic drive that moved those 700-pound boulders wasn't a violent hurricane, it wasn't a magnetic anomaly from the center of the Earth, and it definitely wasn't an alien tractor beam.
It was the incredibly gentle, perfectly synchronized action of paper-thin windowpane ice, morning sunlight, and a light desert breeze. It took a century of wild guessing, but only a few years of patient, perfectly calibrated observation to finally see it happen.
And I think it is worth leaving you with this final provocative thought to mull over. If massive 700-pound boulders can slide hundreds of meters across a flat desert, completely unnoticed by humanity for thousands of years, simply because we were not looking at the exact right moment with the right instruments, what other invisible slow-motion geological processes are currently happening right beneath our feet?
The Earth is constantly in motion. Mountains are rising, continents are drifting, and landscapes are being engineered by microscopic forces.
Yeah.
We're surrounded by natural miracles, just waiting for the right combination of human patience and modern technology to finally be seen.
The stage is always set, the actors are always moving, we just have to learn how to watch the play. Keep looking closely at the world around you.